All right, lesson number 2. So we're picking up right where we left off. We started talking about momentum. I taught you guys that momentum is equal to mass times velocity. Momentum is a vector. We use the letter P for it. Units are Newton seconds or kilogram meters per second. And then we went through and we did 2 example problems. So we're going to pick up, while I'm going through this, by the way, I don't think I explicitly said it, you guys have the packet yourself, so you can just play this video on your laptop and take notes just like if I was talking to you guys at school. Perfect. So here we have a continuation of the problem we were working on yesterday, but now the dart has already been fired. It is in the air, it is traveling with a speed of 1,100 meters per second, and it is going to collide and stick in a block of wood that is 6 kilograms at rest on a table. The block will then slide without friction, and we want to know with what speed will it slide. So essentially, it's a collision. So we're going to still stick with the fact that we know the momentum is going to be conserved in this collision. However, unlike the previous example, there is initial momentum. That dart is traveling. So the initial momentum is the mass of the dart times the speed of the dart. And then after the collision, the dart and the block have become one object that is going to be traveling one common speed v. So they are combined, so it's the mass of the dart plus the mass of the block times a speed v. And that's what we're trying to figure out. We're trying to figure out what is that speed after the collision. Well, I know all the variables. I know the dart is 0.05 kilograms and traveling 1,100 meters per second. It's going to equal the combined mass, 0.05 plus 6, times the speed that it's traveling. So the speed after the collision is going to be 9.09 meters per second. So after the dart has collided with and stuck to the block, the speed afterwards is going to be 9.09. I don't know if you heard me giggle in the middle of that. My cat decided that now is a good time to jump onto the desk and start eating. Here, let's see. Really? He's chewing. I don't know if you can hear him chewing. Hi, weirdo. And then the dog's just hanging out on the bed. Okay, let's do the next page. I'm sorry if you can hear him eating while we're talking. It'll be fine. Alright, so the next example problem we're going to do is now we have a 10,000 kilogram railroad car traveling at a speed of 24 meters per second. It is going to strike an identical railroad car that is at rest. So let's draw this. Well, that is a very crooked line. That is a little better. So we've got one railroad car traveling 24 meters per second. And then it's going to collide with another railroad car that is at rest. So after the collision, so this is the before. So now we can go like this, and then we'll draw the after over here. They say that these cars are going to stick together because of the collision. So here's car 1. It is connected to and stuck together with car 2, and the two of them are going to travel some speed after. So again, I told you guys that conservation of momentum is what we're going to look at. Momentum initial is going to equal momentum final. So why don't you guys take a second, pause the video right now, See if you can figure it out. What is the initial momentum? Create an expression for it. What is the final momentum? Create an expression for it. Solve for it. What is the speed after the collision? And then once you figure that out, press play and I'll show you my answer. All right, press pause. I'm pausing, but I don't think I need to pause. You guys are pausing the video. So I'm going to just start answering it now. Hopefully you actually paused it and did the problem on your own. Initially, we have the one railroad car moving. It is traveling with some speed. So it's mass of 1 times v of 1, plus the second guy's at 0. So there is no momentum of the second railroad car. So if you wanted to write plus 0, you could, but it doesn't really matter. And then after the collision, they are now one big object traveling at some speed v. So it's 10,000 times 24 is going to equal 20,000 times the speed. So the speed that you get is going to be 12 meters per second. Yay! That should make sense. It's twice the mass, so it's going to be half the speed. This is not always going to be true. If the masses aren't equal, then the speed won't be exactly half, but you would just plug in whatever masses that you have and you will get your answer. The trash truck is now outside. It is very loud in here. I'm going to end this video and I'm going to keep going because this is very loud. And I don't think I can just pause it, so I have to stop the video altogether. Alright, I'm going to stop it. That's part 1. Once the trash truck is not on my street, I'm going to do part 2. Okay, bye. Alright, well, I'm back. That was a little bit crazy. I'm sorry. And then, of course, another trash truck came down the street afterwards, so I had to wait for a little while. But we're back, and I think I'll be able to splice the two movies together. We'll see how that works. I don't know. Anyways, last page of notes that I wanted to do for today is another type of conservation of momentum. We got a situation here where we have a man. He's got a mass of 70 kilograms. He's going to stand on the front end of a flat railroad car, which have a mass of 1,000 kilograms and a length of 10 meters. So 70 kilograms, 1,000 kilograms, 10 meters. The railroad car and him are initially at rest relative to the track. So nothing's moving. The man then will walk from one end of the cart to the other at a speed of 1 meter per second relative to the cart. We're going to assume that there is no friction in the wheels of the railroad car, and we're going to figure out A, what happens to the cart while the man is walking, B, how long does it take him to reach the other end of the cart, and C, what happens when the man stops at the rear of the cart. So the first thing, maybe not intuitive, but when the man starts walking, the cart is essentially going to recoil under him and move the opposite direction. So as he's walking in this picture to the left at 1 meter per second, the cart is going to move to the right. The cart's not necessarily going to move at 1 meter per second. We have to figure out what speed is the cart actually going to move, and that's how we can figure out how long it takes him to reach the other end. One of the reasons the man and the cart will have different speeds is because they have different masses. So for A, what we can say is what happens when the man is walking? The cart is essentially going to recoil. So the cart will, quote unquote, recoil and move the opposite direction. Move the opposite direction of the man. Of the man. Awesome. Now we want to figure out, okay, how long will it take the man to get to the other side? Well, what we can do is figure out first, how fast is the cart going to be moving? And in order to do that, we're going to set up conservation of momentum. Momentum initial is going to equal momentum final. Now, initially, nothing's moving. The man's not moving, the cart's not moving, we're all just at rest. The final situation is the fact that because the man moves, the cart will therefore recoil. So the final momentum is the momentum of the man, so mass of the man times speed of the man, plus the momentum of the cart, m of the cart times speed of the cart. And we're trying to figure out what speed does this cart recoil with. All right, so plug it in. Mass of the man was 70 kilograms. The speed of the man, be careful. Momentum's a vector, you need direction. So it's going 1 meter per second, but in the negative direction. So it's -1. Plus the mass of the cart is 1,000 kilograms, and we're trying to figure out what is the speed of the cart. All right, go through. All the variables are now plugged in except for speed of the cart. That's what we're trying to get. The speed of the cart is therefore 0.07 meters per second. So as the man walks to the left at 1 meter per second, the cart is going to recoil to the right at 0.07 meters per second. But that's not the answer, or that's not the answer, because that's not what the question is. The question wants us to know not how fast is the cart moving, but how long does it take the man to reach the other side. Okay, well, we know speed is distance over time, or displacement over time. We're trying to find time. We know the cart is 10 meters long, but what's the speed? So if you think about it, as the man's walking to the left, the cart's going towards the right, so the cart is moving under him faster. The speed of the man relative to the cart is actually 1.07 meters per second. It's going to equal the 10 meters divided by the change in time. And therefore, it's going to take him 9.346 seconds. If the cart could not move, it would take him 10 seconds because he would walk 1 meter per second for 10 meters, and it would therefore take him 10 seconds. But because the cart is recoiling under him, he's essentially moving faster relative to the cart, so he gets to the other end quicker than the 10 seconds it normally would take him if the cart was not recoiling. Does that make sense? I hope so. Let me know if it doesn't. And then part C says, all right, what happens when the man stops at the rear of the car? Well, then the cart's going to stop. If the man stops, the cart's stopping. The only reason the cart was moving was because the man was moving. So C, the cart also stops. The man stops, the cart stops. The man moves, the cart moves. Awesome. All right, so good job. We went through 3 pages today. The next couple pages are practice problems, so your assignment will be to work on those. You won't be watching videos and taking notes. You'll be practicing them on your own. And hopefully this is working for all of you guys. I'm sorry it's not in class, but hey, we're making do, right? Let me know, email me any questions or concerns, and enjoy the rest of your day. Bye.